Hello, my name is Allison Picha, and I'm the CTO and co-founder at Mango Materials. Our work at Mango Materials is loosely based on my PhD work at Stanford University, where I studied the production of PHA from methanotrophic or methane-eating bacteria. At Mango Materials, we are largely focused on replacing plastics with PHA, but I'm here today to tell you about an exciting new application that we've been working on with Schmidt Marine Technology Partners. And now I'd like to talk about a specific application for PHA in aquatic environments. With funding from Schmidt Marine Technology Partners, which is a program of the Schmidt Family Foundation, Mango Materials has developed an innovative biopolymer-based solution to reduce excess nitrogen in aquatic systems. Although living organisms require nitrogen to survive, excess nitrogen can cause algal blooms, eutrophication, and other problems in aquatic ecosystems. At Mango Materials, we make PHA, or polyhydroxyalkanoate. Specifically, we make poly-3-hydroxybutyrate, or P3HB. And we consider PHA to be a naturally regenerative solution. We make next-generation PHA biopolymers that address global warming and prevent plastic pollution in the process. PHA is fully biodegradable and compostable, leaving no toxic traces behind. It's also customizable and designed for the circular economy. Now here I show you the stoichiometry that illustrates how PHA can be used for nitrogen removal. In the top equation, you see this is an example of denitrification, where PHA is represented by C4H6O2, and on the left side of the equation, it helps to remove the nitrate, also on the left side of the equation, and in the process, biomass on the right side, shown as C5H7O2N, is produced. The theoretical requirement for PHA is 3 kilograms of PHB per kilogram of nitrate as N, and we believe that more work is required in order to fully understand the stoichiometry and eliminate any potential uncertainties here. Through our work, we demonstrated that the biopolymer PHA can measurably reduce detrimental levels of nitrogen in aquatic ecosystems in numerous ways. One, we believe it accelerates the removal of nitrogen by serving as a carbon source for microbes that remove nitrogen pollution. And two, it may promote biofilm growth that can aid in increasing overall biomass. One aspect of our study focused on whether PHA could be added to a standard wastewater treatment plant to increase nitrogen removal. We obtained water samples from a local wastewater treatment plant. Because standard wastewater treatment comprises several stages for physical and biological removal of pollutants, we obtained samples from different steps in the treatment process. In a key experiment, experimental microcosm systems with and without added PHA powder were set up using anaerobic sludge and secondary wastewater effluent. After they were incubated, we monitored their ammonium concentrations. In microcosm flasks that had added PHA, substantial biofilm formation was visible on the sides of the flasks near the liquid-air interface. Biofilm formation was not observed in flasks that did not have PHA added. One plausible explanation for this finding is that bacterial biofilm growth is stimulated when PHA is available as a carbon source. In secondary effluent, the presence of PHA significantly reduced ammonium concentrations after 3 days of incubation. Secondary effluent microcosms with PHA added had concentrations of ammonia that were over 50% lower than secondary effluent microcosms that did not have PHA added. Initially, we had predicted that seeding the system with bacteria that had been previously exposed to PHA might be needed to help accelerate nitrogen removal. However, we found that microbes capable of PHA-accelerated nitrogen removal were already present in the secondary effluent, making seeding unnecessary. Based on these results, and in combination with extensive discussions with wastewater treatment plant operators, our findings suggest that secondary effluent is an ideal location for adding PHA as a treatment to reduce nitrogen. Deploying PHA in secondary effluent would be simple due to the modular holding tank infrastructure that allows for varying retention times and optimizing the process. To gain a deeper understanding of the potential PHA demand for nitrogen removal, we conducted market research in areas that include wastewater treatment, aquaculture, and golf course management. In wastewater treatment, while regulations vary regionally, there is deep concern that future regulations may limit nitrogen content of wastewater effluent. In an uncertain regulatory environment, we found from many discussions that wastewater plant operators and managers preferred a recurring expense, such as the recurring purchase of PHA granules, compared to large capital investment in new nitrogen removal infrastructure. Through contact with managers at top golf courses throughout the U.S., This revealed information about nitrogen removal efforts within their ponds and lagoons. There are vastly different climates and regions across the U.S. that influence the approaches taken locally regarding maintenance of ponds. Some places use chemicals to prevent algae growth, whereas others take a more integrated management approach, such as using fish. Although nitrogen pollution was cited as a concern, systems for nitrogen removal in ponds were not always present. Based on the interest shown in an environmentally friendly solution, we believe the opportunity exists in areas other than wastewater treatment for a non-invasive, non-toxic, PHA-based solution for nitrogen removal. Now I want to thank you for your attention, and if you'd like to have any further information on the use of PHA for nitrogen removal, you can visit us on our website and contact us through an inquiry there, or you can email us at info@mangomaterials.com. Thank you so much.